This is a lecture on the very important topic of change of variable in multivariable calculus. In single variable calculus, change of variable is called substitution. And having understood substitution in single variable calculus, you would like to think that gives you a basis for understanding this change of variable in multivariable calculus, but that's not necessarily the case. It's really easier to start with functions of two variables and double integrals. And I'd like to point out the reason that single variable calculus doesn't give you a lot of insight into multivariable calculus in this topic, because then you won't be confused when you start seeing how things are written, or this might point out to you how things are written differently in multivariable calculus. In single variable calculus, that would be some function of one variable like f of x. We might have an integral which is difficult to evaluate. So we use a substitution. And observe how we write this substitution. We write new variable, and that's the u, is some function, we'll have tilde to make it be different, of the old variable. And then of course we have to do change the variable, the differential, and then we end up with something that's very easy to evaluate, hopefully. When we get to functions of several variables, we don't write the old variable u in terms, the new variable u in terms of the old variable x. Instead, we write it the other way. We write the expression as the old in terms of the new. These equations would be for a function of three variables. You start out with a function of x, y, z. I'll put a tilde on it to make it different from that f. And you want to change from x, y, z to some new variables u, v, and w. So we write the old in terms of the new. Here's the old y in terms of the three new ones, and the same for z. For two variables, of course, you only have to change from x, y to two new variables, which I'll call u and v. Here's an example. Say we're trying to evaluate this double integral. All right, which actually isn't that hard to integrate, but let's just say you want to change it to other variables. We want to change it, for example, to polar coordinates. To do that, we write the old variables, here's my x and y, in terms of the new variables, which are r and theta. The remainder of this discussion will contain geometry and will also contain some analysis, and it is very long and involved. The total discussion is. All I'm doing is sketching out a pathway for you through this discussion. I recommend that you go to whatever text you're using, Stewart or Thomas, and look through their examples and try to figure out what this really means. The bottom line, though, is that you don't need to really understand what it means. I hate saying that, but it's kind of true. All right, what you need is to understand what a Jacobian is. And when you understand the Jacobian, then you can take a double or a triple integral, change its variables properly, and be able to evaluate it using new variables. So here's the idea, and I'm going to start with a little geometry. When you have a double integral, remember that you're really taking the volume. And the volume consists of these rectangles, and you want the height of the rectangle times the area of the base of the rectangle. And the height of the rectangle is given by the function value in the box. I'll put stars there, meaning that's in that particular box, times the area. And the area is dx times dy. With that idea in mind, now let's look at a change of variable. So we're changing xy into uv. We will have a function, so we've got some double integral, and we have some function of xy, and then we have dx dy, that representing the area of the base. When we change xy to uv, it's fairly straightforward to rewrite the function in terms of the new variables. But the real problem is what happens to the area of the base. What happens here, the dx dy. So to find that out, I'm going to write the equations like this, which isn't exactly the proper notation. I'll say the new x is written in terms of new variables and y is written in terms of the new variables. For example, you might say that x equals, well, u squared plus v. Now x is written in terms of the new variables and y is 4v. Okay, so these functions are then grouped into a vector. The x changes in the I direction and the y changing in the j direction. We'll call it vector r. This slide shows what happens and what can potentially happen at the base of those rectangles for those Riemann sums, the base of those boxes for Riemann sums. We don't think about this when we're working with functions of one variable. But here we have a function of two variables. We're talking about some function of x and y, and we're changing the variables from x, y into, in this case, r and theta, although they wrote phi up here in this graph that I got from somewhere. Alright, look what happens to the shape of the base. In this case, say xy was a semicircular disk, this half washer here. With a change of variable, it can become a rectangle, which is easier to integrate. You could think of it the other way. You could think that this rectangular region, which you would like to integrate over, is warped from here into that area in the xy plane. That's why this arrow is double-headed. This idea comes up in a homework problem in which an ellipse is warped with a change of variable into a circle. Circle is, of course, easier to handle than an ellipse. Here's another scan showing the same thing again, but this time here would be the new variables shown as a nice rectangular region, and here are your x and y, your old variables or original variables, and they say they map out some sort of a non-rectangular region. And so we're going to take this nice rectangular region and map it on top of here. And the question is, if you remember, we have function of x, y, dx, dy, that's giving me the area. This becomes the function of uv. And what happens to this area? We're going to have to write a new term for the area in order for the integral to come out right. Now the a and b, these a and b vectors represent the nice rectangular area superimposed on top of the original region R. What is the area? Area enclosed by two vectors, remember, can be written as a cross product. A cross b gives me a vector perpendicular, orthogonal, to the plane created by the two vectors. The length of this vector, the magnitude of that vector, is the area enclosed by the vectors. So I want this area, and it will be A cross B. I've just written A and B, and I haven't specified them. I need to write them in terms of the old and the new coordinates so I can make this transformation. So if you remember, I wrote a vector R like a parametric vector in terms of this coordinate transformation. So I have a reference point here, and in B I move a distance delta V and pick up another point here, and the difference between those makes my vector A. Same here for the A direction, or for my vector B. In the other direction, I move a distance delta U, and the difference makes up A. Well, if you look at these terms, they look very similar to terms that appear in the difference quotient. So if I write them, I write the difference between those two terms, which would give me the A vector, and I divide by delta U, that is the difference quotient. In the limit, as delta U goes to 0, I get the derivative of R with respect to U. Similarly, if I take the difference between the reference point and the vector where I've added delta V to it and divide by delta V, then I really have created, in the limit, the partial of r with respect to v. I'm going to rewrite these. Of course, the numerators were a and b, the vectors a and b. So now I can write a as delta u times the partial with respect to u, and b is delta v times the partial with respect to r and v. So I'm finding these vectors that are going to define the sides of this new rectangle. I'm finding them in terms of the old and new coordinates. So here we see these pictures again. Although this area, the blue area underneath here was R, the original region, and here is this superimposed nice square region. It's sort of lifted off of here compared to that first diagram that you saw, but that's just so you can see it. Okay, so here's my reference point. This was a vector A, and this was a vector B. So the area was A cross B, right? And so I can write that. I will have delta U, it's a vector, it's a partial with respect to U, cross delta V times the partial of that vector with respect to V. Of course, these are constants. I can pull them to the outside, and I just have the cross product of those two partial derivatives. And writing out those partial derivatives, the partial of r with respect to u is the partial of x with respect to u in the I direction, plus the partial of y with respect to u in the j direction. And for the other partial derivative, I have x with respect to v and y with respect to v. You don't have to know this derivation for this class, but you have to know the punchline, which is coming up real soon. And here's what you have to know. When you change that variable from dx dy, and you change it from x and y into new variables u and v, that change is given by du times dv times this term, which is that the determinant of the cross product. So here's a cross product. Of course, we don't have any k variables in this, and it just reduces to this determinant times du dv. This is called the Jacobian. If you just have the matrix itself, it's called a Jacobian matrix. When you take the determinant is called the Jacobian. There's also special notation for it here with the two partial signs, and then in parentheses you have the old variables and in the numerator, and the new variables in the denominator. So here's a Jacobian. Say you were going from xy to r theta, it would look like that. And this would be the determinant, and we'll see more of these in a minute. If you took the partial of x with respect to r, partial of y with respect to r, here you would have the partial of x with respect to theta, and the partial of y with respect to theta, and that's what that notation means, and that is the Jacobian. You could also take the transform of this matrix, because it wouldn't matter. So here's the double integral. This is what we're talking about. We have the function, here's the original formulation in terms of the old variables x and y. I'm going to write that on here. So here's the old original variables. Now we transform to u and v. The function is just rewritten as f of uv. But this area dx becomes a new area, which will be du times dv, and then you have the scaling factor of the Jacobian. And the Jacobian is the determinant of this matrix of partial derivatives. Because all you care about is the determinant, you can write this matrix, the transpose of this matrix. So instead of having partial with respect to x, an x and a y here, you could do the x with respect to u and the x with respect to v, and then in the second row, y with respect to u and y with respect to v. You'll get the same determinant. Sometimes it's handy to write it one way or the other, with no geometry and no derivation, because it's very hard to draw. Here it is for the triple integral. So you start with a function of three variables, we'll call them x, y, and z, and you transform to some new variables u, v, and w. The area here, or the volume, dx dy dz, becomes du dv dw multiplied by the Jacobian. Here's the Jacobian right here. And the Jacobian, again, is the determinant of the matrix of partial derivatives. Let me repeat again what you have to know. I gave you this derivation with all the geometry and changing that basic area around in order to give you some insight into what's going on. Although I'm sure what I presented is not a complete derivation. You really have to sit down and work through the different pictures yourself, looking in Stewart or in Thomas. But what you do need to know is this idea right here. You need to know how to change the variable in 3 and in 2 dimensions, and that's how you do it. You take the function, you have your original function, you write x, you write your transformation in terms of the old into the new, however you want to change it, or however it's suggested you change it. You rewrite the function in terms of the new variables just by substitution. You compute the Jacobian by making the matrix of partial derivatives and taking the determinant. That multiplies du dv dw. This is actually a triple integral, and I don't know how that slipped past. And it's the same thing for the double integral. Here's what you have to know for the double integral. You start with an original formulation of the problem in terms of x and y, and you want to change to some new variables, u, v, which may be polar coordinates. That's very frequent. So you write x in terms of the new variables. You write y in terms of the new variables. You take the function and rewrite it by substitution, just substituting in for u and v, and you find your new variables, your new function. Then for the dx dy, that is replaced by the Jacobian, which is the determinant of the matrix of partial derivatives, times du dv.